Hey guys, in this State of the Mill video I want to talk about the new motor for the G0704. A few days ago I posted just a short video with some sped up footage of me building the temporary motor mounts and getting the motor mounted, and now I just want to talk about the motor. So this is a Marathon Electric. It's the model Micro Max, and it's an inverter duty 1.5 horsepower motor. It's 3-phase AC, and at 60 hertz it's 1,800 RPM. Now the reason why this one's called inverter duty, and some motors say that, but they're not true inverter duty like this one is, it has a 1,000 to 1 torque rating, which means I can pull the full 4.8 amps from 0 all the way up to 1,800 RPM, and this motor can take it. It has an H1 or a H-class insulation rating, which means this thing gets screaming hot. It's sealed, it doesn't even have a fan, but it's made to do it. So this thing's gonna produce awesome torque, and part of the reason why I ended up with this motor was because it basically means I can't burn it up. If I'm doing a cut at 1,800 RPM, torque is gonna be there all the way down to 0 RPM. So this thing should be pretty awesome. The cool thing is that 1,800 RPM is 60 hertz, and it's actually rated full horsepower up to 120 hertz, so that's 3,600 RPM. Max safe RPM is 5,400, which means this thing will actually run up to 180 hertz. Now, of course, horsepower is going to fall off dramatically between 120 hertz and 180, and I probably won't run it above 120 anyway, but it's cool to know that it can do it. So let's see, I think I mentioned it's 4.8 amps, 230 volt, 3-phase AC. On the top there, it has, see that dome? There's a dual channel quadrature encoder, came included with the motor. And shockingly, this 1.5 horsepower motor retails for about 900 bucks. Now I picked mine up for $200 plus 100 shipping from the East Coast, and I felt like that was a screaming deal, and I just couldn't pass it up. The encoder alone to replace it is about $500. And the way I found this motor is actually from my buddy Ben, and if you guys are on Instagram, here's his Instagram account. Check the link in the description. Ben's. He has the G0704. His runs at 10,000 RPM. He's done some pretty cool mods, and he's building something called the Freedom Light, which is awesome. Here's a screenshot. His website is freedom.lighting. Isn't that weird? There's no .com. It's just freedom.lighting. And you need to follow him on Instagram. He does some really cool small end mill, high RPM 3D profiling. For a G0704, he's really making some awesome stuff, and he's prototyped the crap out of this light. It's awesome. Go support him on Instagram. I think there might be a Kickstarter in the future. I'm not 100% sure. And he's actually working on a collaboration with Brad over at Tactical Keychains, Brad's Instagram. And go check Brad out also. You guys, I've sent you there several times. Anyway, thanks Ben. If it wasn't for your link for the surplus website, I would never have found this motor. Check the link in the description for all that, plus the link to the motor. As of today, which is July 20-something, 2016, there's like 27 of these still available from that website. So they're new in-box surplus. Pretty awesome. Now, one thing I want to point out real fast, this 1024 pulse per rev encoder is too fast of a pulse stream for Linux CNC to deal with. It seems like, from what I've been reading, it's pretty difficult to software count, pulse count above 50,000 hertz. And my pulse stream is going to be quite a bit faster than that. I can't remember, like 5 times as fast at top RPM. So I've already done some testing, and basically I can only go up to 1,300 RPM spindle speed, which is somewhere around 700 RPM motor speed. And then Linux CNC can no longer keep up, and my RPMs go totally crazy. There's a couple of ways to overcome that. One way is to do what's called a pulse divider using a hardware counter. And there are these little circuits, they're like 60 cents, and I could buy a couple of those to, I'd need 3 for each of the quadrature channels. And then I could reduce the pulse stream down to something like, I think it'll divide by a factor of 12. So I could get down to what, like 8 pulses per rev or something like that. And I could send that to Linux CNC, and it would totally handle it. That's a really cheap, easy solution. The other idea is to go with a Mesa PCI Express and daughter card. That also means I'll need a new computer, or a newer computer. The cool thing about going that way is it'll handle a pulse stream up to like 4 megahertz, which is crazy fast. And then also those daughter boards give you like 32 inputs. Now my C11 breakout board's been awesome, but I only get 4 inputs. So for instance, on my lathe, my spindle has the index pulse, the multi-pulse, I have my home and limit switches on one pin, and then I have an e-stop on another pin, and I'm out of pins. If I went with the Mesa setup, which is about 200 bucks, in fact, link in the description if you're curious. Yeah, it's quite a bit more money, and I'm probably going to do it in the future, but I like the idea of getting all those extra inputs, and also it being able to handle the pulse count for this high resolution encoder. Also, one more thing about that Mesa setup, it's the same one that Tormach uses, so if you want to run Path Pilot, that's the setup you need to get. This is the chunk of aluminum I was machining when I burned up the DC motor, and I was using this 3/8 inch high-speed steel, high helix end mill, and it was cutting really good, it sounded nice, and then all of a sudden it started to sound like it was slowing down. I thought maybe the coolant just wasn't getting onto the end mill, so it happened to be on the back side, so I adjusted my coolant flow and it still continued to slow down, and by the time I could reach over and hit the e-stop button, I blew the fuse in my on my DC drive. I had the wrong fuse in. I should have had about a 12 amp fuse. I had a 25 amp fuse, and by the time I hit the e-stop, the fuse blew and there was fire and smoke coming out of the top of the motor, so I knew it was done for. I'm going to go back into Feeds and Speed Wizard and find out what's going on. I was doing an 1.25 inch almost depth of cut, 20 thou step over, 7,200 RPM, and my feed rate was initially 15 inches per minute, but it was giving me just a ton of chatter. So I kept bumping up the feed rate until I got up to 200% or 30 inches a minute, and the cut quieted down, the chips were coming off, they looked great, and then everything kind of, burned up. So that ends up being about 3/4 cubic inch metal removal rate. That's pretty good for this machine, actually. It's pretty good for, an end mill like this. So I'm satisfied with the cut. I just, burned up a motor trying to make it. So if you watched that earlier video, and you can see, click the card right there to go back to that one if you haven't watched it. I made my own pulleys. I took the original toothed belt pulley that was on the old motor, and I turned it down into a splined belt, or a timing belt, or not a timing belt, but a serpentine belt style. And then I made this pulley from scratch with a chunk of 2-inch aluminum. The main reason why I went this route is because this belt setup is quieter than the timing belt, and also the belts are way cheaper. So for instance, this is a 6-rib belt, here's a 4-rib, and here is an 8-rib. I ended up going with the 6. If I go with a 2-speed pulley setup, which I plan on doing in the future, I may go with the 4 ribs. If any of you are running 4 ribs, I'd be interested to hear if you have any slippage issues. Anyway, these are like $1 a piece. I think I paid like $4 for all 3 of the belts, and then it was like $8 shipping. Whereas the timing belt, this style of belt, this is about a $15 belt. So, at least 10 times the price, and quite a bit noisier, and I just don't think I need the positive lockup. Eventually I may try rigid tapping with this once I get the encoder situation solved, but even then I think I'm going to get plenty of holding power with the ribbed belt, so I guess time will tell. As I've mentioned before, I'm controlling both the mill and the lathe from my single enclosure cabinet, and the way that I'm doing that is I've routed everything through relays and switches. So basically, this switch here, if it's pointing at the lathe, it means I'm powering the lathe motor. If this switch is pointing at the lathe, it means I'm reading the lathe encoders. So all I have to do is, as long as the motor doesn't have power to it, VFD can still be on, and now it's running the mill. So that worked out really nice. Let me show you what it looks like inside. You can see I got rid of the DC drive and installed the second bank of relays. So basically there's 2 relays going down here that power the VFD, and then power comes from the VFD up to this relay bank, where 3 relays go to the lathe motor and 3 relays go to the mill motor. So I just have to flip a switch, it decides which relays. The switches I showed you, those are on. Let's see, those are double throw, double pull, so they're on DPDT switches. And yeah, really cheap, easy to work with. These relay boards, they'll support like 10 amps per relay. So I mean, we could go up to, what, 10 horsepower? and 3 horsepower, and they're only a few bucks on Amazon. They're really cheap. Just Google, go to Amazon and do a search for relay module, and these will come up. They're everywhere. Tons of people are selling them. So the other thing that's kind of a bummer is I actually do have to change a couple of programs on the VFD when I switch between lathe and mill mode. It's actually less than what I thought it was going to be, so I made this little cheat sheet. You can see I have to change program 5 for the mills, 120 hertz. It's 60 hertz for the lathe. So I actually just did a few tests at 120 hertz on my lathe motor. It's not rated for that, but I figure the really only 2 things we need to worry about are bearings and heat. So small bearings like the ones that are going to be inside this motor are probably rated way over 1800 RPM. That would be a really low rating for a bearing, especially, you know, a Leeson motor. They're good motors, so I expect they probably have pretty good bearings in them. I think the main problem is heat, and so I have a 120 millimeter computer fan. It's an AC powered fan, and it has pretty high flow, and I'm going to mount that behind the motor. I'll do some heat soak tests and read it with my temperature gun and find out what temperatures I normally get at 60 hertz, and then I'll slowly bump it up and see what the temperatures go to. I'll try out this this 120 millimeter fan, which I plan on using mostly for low RPM situations. That way at low RPM I still have plenty of fan speed. Anyway, so I have to change the hertz. I have to change the max motor amps, which is program 142. So 3.2 and 4.8 on the mill. Then programs 144 for the belt drive. These are my 3 belt drives in high range on the lathe. I almost always stay on in high range, the slowest speed, and that gives me about 800 RPM. I'm fine with that. But if I could run it at 120 hertz, that'd give me 1600 RPM, so that could kind of be cool. And then eventually I'll have 2 speeds on the mill, so I've, you know, left a blank there. But yeah, I shut off the motor, I changed these 3 programs and restart Linux CNC. Actually, I have to switch between my lathe config and my mill config anyway, and then flip those 2 switches on the front. We're in business. Okay, so I have everything turned on. I'm going to show you the slowest and fastest speeds I can manage right now. Unfortunately, I didn't realize this earlier, but with the Modbus communication to Linux CNC, between Linux CNC and the VFD, you actually don't get infinite RPM speed control. It moves in steps, so that's actually kind of frustrating. If you want infinite adjustability, you need to use the 0 to 10 volt drive method and not Modbus. The reason why I went with Modbus is because I don't have to use any inputs on my breakout board. Whereas if I go with the other method, I have to have at least 1 input just to switch between forward and reverse, and I don't have an extra input. So unfortunately, we're stuck with this until I probably go with that Mesa setup, or if I decide to build the pulse divider card. I'll do a whole video on that, by the way, if I go that route, but I probably won't. So here's the lowest RPM, which is 430, and I'll speed it up to 6,500. So kind of a short demo, nothing too exciting. I'm going to get back to trying to machine that chunk of aluminum, and yeah, I guess that's all for now. Alright, I want to try something real fast. I've got the acceleration times and deceleration time set up to 2 seconds. I'm going to speed it up, let it hum for a second, and then shut it back down. And then I'm going to do the test again, but I'm going to change those programs down to maybe like a half a second just to see what happens. So here it is, ramping up and down at 2 seconds. Okay, deceleration's not going to be affected because the drivetrain has to slow down at whatever natural speed it can. I don't have a braking resistor. Frankly, I don't know anything about them, and I'd like one, but I just tested it, and yeah, this thing starts up way fast. I'm going to go ahead and do the exact same test you just saw. Yeah, I might have to leave it there and try it out on my lathe, because that's pretty exciting. Actually, I am going to go try it out on my lathe. Okay, so I've got acceleration and deceleration back at 2 seconds. We're going to go up to 60 hertz because that's all we're going to run right now. Let's see what happens. Okay, I'm going to drop that down to half second acceleration from 2 seconds, and we'll see what happens. Oh my, this is shocking. I should have been doing this all along. Here we go, half seconds. Speeds it up and slows it down insanely fast. I don't know why I've been doing it as 2 seconds this whole time. I guess I was afraid of overloading it during startup, but I mean, it's not like you start and stop it 1,000 times in a row, so it's probably not that big of a deal. Anyway, that's it for this video, guys. Thanks for watching, and I'll see you in the next one.